Hello, good afternoon. Viva, muito boa tarde. It's wonderful to see this auditorium, José Mariano Gago, full of physicists, mainly, but with teachers, high school teachers and students and youngsters. That's wonderful. Thank you for coming. I will open the session in the name of my team, Ciência Viva, and I would like to welcome Fabiola. It's a great pleasure to receive you here. And dear Mário Pimenta, the president of LEAP, and our compliments also to the all scientists from LEAP, Patricia and others. You are so many and so good. Dear Alexandre Quintanilha is our MP, a scientist MP. Who don't want to have scientists MPs? And you are very fortunate to have you at the Parliament. Dear scientists, dear colleagues, dear participants, we have participants also following this session at the website, so online, and we apologize to be waiting so long, but it will be a great session, we can assure, so it's very good to know that you are there. Ciência Viva has a long-term relationship with CERN and, of course, with the Higgs boson. In fact, LEAP was the research laboratory created by the founder, José Mariano Gago. This auditorium has his name, as you know, and LEAP is one of our associated members. And this has always helped us in our relationship with CERN. Thank you, dear Mário, and your team. So we are particularly happy to have you, Fabiola, with us today in this auditorium. And so we started tracking the boson in 2010 with a live transmission commented by Portuguese scientists of the first tests of the LHC and the first collision in April. All very exciting on that time, you can imagine. 2012 was a special year for the boson. Everything you always wanted to know about the boson was in August and was the title of a large event for the public and journalists. Later, in October, in the same year, 2012, we organized the Science Café at the Portuguese Parliament on the societal benefits of big boson, with MPs, scientists, entrepreneurs, and students. A very lively event, as you can see in the picture. I should move the picture. Here we are at the Parliament with this discussion about so important issue. Do you remember? I'm sure, yes, you are with us, Alexandre, since the beginning of these science cafés. We maintain still this relationship with the politicians, which is much more needed, much more than ever. And later, on that time, we distributed a kind of a toy. We can say really a toy. Is called in English a paper fortune teller. Is this, do you remember? Quantos queres in Portuguese? Isto devia funcionar bem. Quantos queres? Now, we made it to each participant of that science cafe at the Parliament. Quantos queres? How much you want? And open and find the information inside. And everything went to the X in the middle with this kind of information. We made it to that science cafe at the Portuguese Parliament. Also in collaboration with LIP, of course. Is this one. It was very, very interesting, this paper fortune. Quantos queres? And still on that year, it was a very successful year, 2012. In that year, we had Sergio Bertolucci, on that time, you know, head of research and scientific computation, was the main speaker of our first edition of Christmas conference, Ciência Viva Christmas conference that we are organizing since then, every year. Now, we are thrilled to receive you today, Fabiola, at the Pavilion of Knowledge, to be updated on the research and the societal benefits of our, we can say, shy friend, as Bosón is, I think. Okay. And we are also very happy to continue to contribute to inspire youngsters to this great adventure as the knowledge is. Thank you so much, and is your floor.
Thank you.
Here in the middle.
Okay, good. Thank you. Thank you very much. Thanks a lot for this invitation. It's a great pleasure and honor to be here, in particular in this auditorium named after José Mariano Gago. I don't have to tell you what great man Mariano Gago was and how important he has been for Portugal, for CERN, for Europe. But I say also for me personally, he has always been a person I could always ask and advise, and he has been helping me a lot at moments of my scientific career where I needed the advice of a very wise and welcoming person. So it continues to be in our hearts. So today I'm going to talk about fundamental research, which sometimes scares people. It looks something like very far away, and also but with the aim of trying to explain the importance of fundamental research for our life. And I will take the Higgs boson as an example, because this little special particles actually is responsible for our own existence, and I will try to explain why. So the Higgs boson was discovered at CERN in 2012, as it was previously mentioned, and so I just want to remind you that what we do at CERN is to understand the most fundamental particles of the universe, so the smallest constituents of matter, and the laws of the universe at the most fundamental level. And actually CERN is the biggest laboratory in particle physics. What you can see here is an aerial view of the Geneva region. Here you see in red the border between Switzerland here and France on the top of the screen. This is the Lake Geneva, Geneva Airport, and this white circle shows the location of the Large Hadron Collider, the LHC, the most powerful and biggest accelerator ever built, which is the instrument that allowed us to discover the Higgs boson. So the goal of CERN, as I said, is to study the elementary particles. Elementary particles are objects that cannot be cut into smaller pieces, so they have no substructures. And so to understand really the basic foundation of the universe. So I think that everybody in this room knows that matter is made of atoms. Atoms, in turn, are made of a central nucleus surrounded by a cloud of electrons. Nuclei are not elementary particles because they're made of substructures called protons and neutrons, and protons and neutrons are made of smaller objects called the quarks. And as far as we know today, electrons and quarks are elementary particles. They cannot be cut into smaller pieces, and they are the fundamental constituents of the matter we know. The matter stars, planet, people, plants, animals are made of. So we are all made of electrons and quarks. Even the president of Portugal is made of electrons and quarks. Everybody. And in order to study matter at the level of its fundamental constituents, we need powerful accelerators. So instruments that allow us to accelerate particles, to smash them at a very high energy, so that the smashed particles break in thousands of pieces. This is not rigorous from the scientific viewpoint, but just to give you an idea. And then this allows us to study its fundamental constituents. So accelerators can be seen as very powerful microscopes that allows us to scrutinize matter on the scale, on physical scales of smaller than 10 to the minus 18 meters, so a billions of a meter. And at the same time, the study of the very, very small allows us to understand the very, very big, so the structure and evolution of the universe. And this is because we know today that the universe had origin from a big explosion called the Big Bang, some 13.8 billion years ago. And at the beginning, the universe was very hot and dense, and it was essentially made of elementary particles, free in the original space-time. And so by studying the elementary particles, we can understand the early universe. With time, the universe expanded and cooled down, and with the cooling, particles, elementary particles, combine to form, well, first the quarks to form neutrons and protons, then neutrons and protons to form nuclei, nuclei to form atoms together with electrons. So this movie run in the opposite direction, up to the macrostructure that we know today: planets, galaxies, stars, etc. And there are a few complementary ways to study the universe and its evolution. One is to use telescopes in space or on Earth. So telescopes study the macrostructure, planet, galaxies, etc. And by looking at the farthest objects, they allow us to go back in time. Accelerators actually allow us to study the very first instance of the primordial universe. They allow us to go back to 10 to the minus 12 seconds after the Big Bang. So with accelerator, we are able to reproduce the conditions that the universe had 1 millionth of a second after the Big Bang. And I will try to explain in a couple of slides how this is possible. So to do so, we need colliders, big accelerators that allow us to accelerate two beams of particles in the two opposite directions. So at the Large Hadron Collider, we accelerate a beam of protons in one direction, a beam of protons in the other direction, up to the highest possible energies, where the limit only come from technology, in particular the technology of magnets that are needed to keep the beams on the circular path. And the higher the energy of the beams, the more difficult it is to keep them on the circular path. Like when you drive a car, the higher the energy, the more difficult it is to keep it on a circular race track. And then we smash them. We smash them at the highest possible energy at 4 points of the ring, where in 4 big underground caverns, we have installed 4 big instruments called particle detectors, 4 experiments. Their names are ALICE, ATLAS, CMS, and LHCb. So the Large Hadron Collider is a 27-kilometer ring, 100-meter underground. So on the surface, you don't see the collider. You see cows, you see people, you see a typical thing that you see in Switzerland, in France. Yes. And we started operation in 2010, and 2 years later, Atlas and CMS, the two largest experiments, were able to report the discovery of this new and very special, I will try to explain later on why so special, particle called the Higgs boson. And let me say already at this stage that Portugal contributed in a very important way to the Atlas and CMS experiments and to the computing infrastructure, because actually to do research at CERN to discover the Higgs boson and now to address other important questions, we need three main instruments. The accelerators that accelerate the particles, the detectors that detect the product of the collision, so the two beams collide at the center of the detectors, and the detectors allow us to reconstruct essentially every single particles produced in these collisions, and then the computers to store the data and analyze them. So CERN and its collaborating member states and institutes, including LIP, had to develop cutting-edge technologies in many fields in order to build these very complex and advanced detectors, fields that go from superconducting materials to electronics, cryogenics, vacuum technologies, different instrumentation, big data, and now we are developing quantum computing and artificial intelligence. And as we will see later on, these technologies are transferred to society free of charge. So this is a quite spectacular view of the LHC tunnel, 27 kilometers, 100 meters underground, the single most important component of the accelerator that allowed us to make a jump in energy compared to the previous collider, which was a machine in the US, the Tevatron in the United States, is a set of superconducting magnets that allowed particles to be followed to be kept on the circular trajectory, which have been developed at CERN, prototyped at CERN, and then have been built by three leading industries in Europe, Alstom in France, Ansaldo in Italy, and Babcock in Germany. And this is an excellent example of collaboration between fundamental research and industry, and I will come back to this later on. The experiments are also quite impressive. You can see here the size of Atlas compared to the size of two average human beings. So Atlas is half the Notre Dame Cathedral in Paris, but underground. The other experiments, CMS, has a weight that is twice as large as the Tour Eiffel. So you see also the challenges of building these instruments. And computing is also a very important, the third component of our toolkit of instruments. So traditionally in particle physics, before the advent of the LHC, the computing resources, so disks, tapes, processor, were all stored in the host lab, so CERN. And all the people doing analysis, all the people that scientists collaborating with CERN would access to these resources at CERN. With the advent of the LHC, the huge amount of data, the experiments have already produced 1.5 exabyte of data. And with the huge collaboration, so I will tell you later on that at CERN we have a community of 17,000 people from all over the world, it would have been impossible to localize and all the computing resources at CERN. And so we developed, CERN invented with their partners, what is called the Worldwide LHC Computing Grid. Is a network of computing centers across the world, something like 170 data centers in 42 countries, provided distributed computing and access to the worldwide LHC community. We have a total storage of 2 exabytes and today 1 million processing cores. So we are among the largest producers and consumers of big data in the world. So here a few numbers, not to impress you, but to give you an idea of the challenge. So the magnets that are used to steer the LHC beams and bring them into collision are superconducting, and as such, they work at low temperature. They actually work at minus 271 degrees, which is colder than outer space. The protons travel very close to the speed of light, so they make something like 11,000 turns of the 27-kilometer ring every second. And when the two beams collide, the energy of the collision corresponds to the temperature that the universe had 10 to the minus 12 seconds after the Big Bang. That's why we are able to reproduce the condition, because the energy that we produce corresponds to the temperature and the condition of the very, very early universe. And these temperatures corresponds to 100,000 billion times the temperature in this room. So you see the LHC beam, of course, have a lot of particles at very high energy, so the energy stored in the beams, in each beams, corresponds to the energy of an Airbus 320 at 110 kilometers per hour. So you see the level of challenges that we had to address and the technologies that we had to develop in order to discover the Higgs boson and to do our research. So let me say a few words about the Higgs boson, why it is so important. Because it is the interaction of the Higgs boson with the elementary particles. You remember that I told you a few minutes ago that the fundamental constituents of atoms, so of matter, so of ourselves, are electrons and quarks. And in the early universe, something like 10 to the minus 12 seconds after the Big Bang, these particles interacting with the Higgs boson, actually with the Higgs field, but okay, let's make it simple, interacting with the Higgs boson, this interaction allowed atoms to form, and so matter to form. Why? Because the interaction between these particles and the Higgs boson allows this particle to acquire a mass. This room is filled with photons. There are a lot of photons, which are the quanta of light. And photons have no mass. They travel at the speed of light. And if electrons and quarks, which were massless at the time of the Big Bang, had remained massless, so if the Higgs boson had not appeared in the early universe and with its interaction provided a mass to the electron and quarks, atoms will not stick together. They could not have formed. So the matter we are made of will not have formed in the early universe, and so we will simply not exist. So the first link, there are two main links of the Higgs boson with our life. The first link is the fact that we will simply not be here without the Higgs boson. So it's clear that it played a very important role in the early universe, and it's also probably related to the fate of the universe, because based on what we know about the Higgs boson and the other elementary particles, today the universe is not in a stable state. It's what we call a metastable state, and one day it could decay into a more stable state. Don't be worried, it's not going to happen tomorrow, maybe in a billion years, but most likely we are not in a stable state. But whether or not, and what is the fate, is also related to the Higgs boson. Clearly, so a study of the Higgs boson at the Large Hadron Collider and at future more powerful colliders will help us understand how the universe came about and how it will evolve in the future. So these tiny particles is so crucial. So what is the Higgs boson? How does the Higgs boson appear in our experiments, in ATLAS and CMS? So here you have a graphical image of a collision between the two proton beams coming from the Large Hadron Collider in the center of the CMS experiment. In this event, a Higgs boson has been produced. Once produced, the Higgs boson has a very short lifetime, 10 to the minus 12 seconds. So it decays, it disintegrates itself immediately into other particles, including particles that we are very familiar with, like electrons, for instance. So this is an event where the Higgs boson has been produced and has disintegrated itself into 4 electrons, these 4 orange arrows. And by looking at the energy and momentum distribution of these decay products, we can reconstruct the mass of the mother particle, the Higgs boson. And here you can see in the spectrum of electrons and other particles called muons, you see this nice peak. This is the sign of the production of the Higgs boson at the Large Hadron Collider, in this case in the ATLAS experiment, with a mass which is something like 113 times the mass of the proton. So this is a Higgs boson, and this is an ensemble of Higgs boson produced at the Large Hadron Collider. So the Higgs boson is not the end of the story. Today there are there's a huge number of open questions in fundamental physics, some of which are quite intriguing and important. So I will mention maybe 2 of them. One is the so-called dark universe. So when we look at the sky in the evening, so you can try tonight going out, and you see the nice planets, stars, and galaxies, what we see is only 5% of what is out there. Meaning that only 5% of the universe is made of the matter we are made of, atoms, chemical elements, as we discussed earlier on. The rest, 95%, is a question mark. Means that it's made of forms of energy and matter that we do not know, and for this reason we call them dark matter and dark energy. Actually, dark indicates our ignorance, we don't know their nature, but also the fact that they do not interact directly with our instruments, otherwise we would have understood what their features are, and so we deduce their existence from indirect proofs. So 95% of the universe is unknown. Today is a question mark, and we have no clue. In addition, the 5% which is there, we don't understand why it's there, because based on what we know today, this 5% of matter should not be there. It should have annihilated with antimatter, another form of matter, in the early universe, but at some point, fortunately, the antimatter disappeared, allowing the matter to survive. So you see, there are also many other questions, but these are very important questions, and here you can see in dark blue the question to which a future collider, in particular a future circular collider at CERN, could help provide answer. This answer requires new physics, that is physics that goes beyond our current experimental and theoretical understanding, which is called the standard model. And the Higgs boson is a key actor in this search for answer to the open question because it is related to many of these mysteries. So for this reason, the European community of particle physicists, which meets typically every 6-7 years in different locations, in 2006-7 was here in Lisbon, to develop the roadmap for the field. So what are the next projects we should develop? What are the next questions that we should address? Has recommended in 2020 to fully exploit the Large Hadron Collider through an upgrade of the Large Hadron Collider, but also to investigate the technical and financial geological feasibility of the next possible machine. So you see here again the Geneva region. Sorry, I have to put my glasses on, otherwise I don't see much. Sorry. Here you see the Large Hadron Collider, 27-kilometer ring, and this is the next possible ring, 90 kilometers. So you see the DRHC looks like a toy compared to the next one, okay? Because a bigger collider, a bigger accelerator with much more advanced technology than what we use today at the Large Hadron Collider should allow us to make big progress in answering to at least some of the previous questions. So all these results and all these advances in fundamental knowledge at CERN would have been impossible without CERN itself, obviously. And let me remind you of the history, because it's important to learn from history, and we find ourselves today in a situation, a geopolitical situation, which reminds us a little bit of the post-World War II. CERN was founded in 1954. This was in the aftermath of World War II. Under the push and the enthusiasm of visionary politicians and scientists who wanted to build a European lab, high-level European lab, with two purposes. Number one, bring back to Europe scientific excellence in scientific research, because during the war, due to the Jewish persecution, many scientists had emigrated out of Europe. And second, foster. So in some sense, you see already the very modern mindset at the time. Those people understood that the recovery of the continent, the recovery of Europe, also goes through investment into fundamental research. And the second big vision was that science can be a glue. And so through this new center, CERN, so the new center, could foster peaceful collaboration between European countries after the divides of the war. And so science is a glue, because science is universal and science is unifying, and so science can build bridges. So CERN started in 1954 with 12 member states. Today we have doubled the number of member states, 23. Portugal is one of them. And then we have 7 associate member states. We have observers, but also we have a huge number of international cooperation agreements with countries, non-member states, some of which are really not really on the front line of science and technology. So some developing countries, underprivileged countries. And in this case, our mission is capacity building, to help these countries bridge the gap with the more advanced countries. The budget of CERN is 1.2 billion Swiss franc annual budget, which is the budget of medium-sized European university, or to use more familiar units, it corresponds to 1 cappuccino per European citizen per year. This is the, so when you drink your next cappuccino, you have to think that this is what you give at CERN per year. And as of today, has a population of 17,000 people from all over the world. More than 110 nationalities are represented. Most of them come from the member states, here in dark blue, with a very strong participation, some 200 scientists in total from Portugal. But also we have scientists coming from developing countries, underserved and underprivileged countries. Some of these scientists come from countries that are not the best friends of each other. In some cases, they are also in conflict. And yet at CERN, they work together, motivated by the same passion for science and for knowledge. If you look at the age distribution of these 17,000 scientists from all over the world, you see that the peak is at 27 years. I'm also here in this peak, and I will not move from this peak. Don't laugh, it's not kind. So 27, so most of our population is actually made of students and young postdocs. Not all of them remain in particle physics. There are not enough jobs, or some of them want to do something else. So actually, most of them go somewhere else. They go to the private sector, 50% of those, 45% of those who leave, they go to industry, they go to public sector in other fields, etc. So our mission is to form these young people and to give them all the tools and the talents to undertake a profession in a professional career in another field, and we don't know a priori which one it can be. So for this reason, we have very, very strong training opportunities. At each moment in time, at CERN we train something like 4,500 young people, including physicists, engineers in many, many fields, from electronics, cryogenics, superconducting materials, everything, and technicians. But also, we have a lot of activities for the public, for the general public. So, and also for students, high school students and high school teachers. We used to have something like 150,000 visitors annually, but we received 300,000 requests. So in other words, we can only satisfy 50% of the requests. This means that there is a huge interest in the public in science, and in particular in CERN. And this is why in a few days from now, on the 7th of October, we are going to inaugurate our new Center for Public Education and Outreach, targeting people of all ages, starting at 5 years, or from 5 years up. So here you see this new center is made of 2 tubes and 3 pavilions. We will be able to host up to 500,000 visitors per year, and there will be immersive spaces, exhibition, educational labs for young people, starting with kids 5 years old up to 16. Then we will have a pavilion on quantum physics to explain why quantum physics is so important. We talk nowadays and we develop quantum computers, quantum sensors, so quantum networks. So what is quantum physics and why it's so important? All this in a very simple and hopefully fascinating way for everybody and accessible. So my last but one chapter is the impact of CERN on society. CERN is the place where the World Wide Web was invented and developed. Tim Berners-Lee was to everyone free of charge. The web is available for society free of charge. If it had been developed in a private company, every time you click, you pay. But because it was developed at CERN, you don't pay. But this is only one example of CERN technologies. There are many, many others which find application in several fields. So let me show you a few examples. So I already mentioned the Tim Berners-Lee and the web. There are applications, most of our applications actually are to the medical field. So certain technologies are used to build, have been used and will be used to build accelerators to treat cancers with therapies that are complementary to the usual X-ray therapy. So with using protons, using electrons, and using light ions like carbon ions. CERN electronics is used for medical imaging. You can see this beautiful wrist image scanner, actually X-ray scan, done with CERN electronics. It's 3D color with very, very high resolution and extreme, very huge number of details. You can see here a radiation dosimeter to measure, an instrument to measure radiation built at CERN on board of the International Space Station. There are example also application to an environment. We have, for instance, a collaboration with Airbus which would like to use our superconducting cables for clean air transport. Machine learning, artificial intelligence, we have a collaboration with Volvo for car autonomous driving. So these are only examples of the impact that the advanced technology that CERN develops have on society. Usually when CERN needs a technology, that technology does not exist yet. So that's why CERN, as many other research, centers for fundamental research is a driver of innovation because very often needs advanced technology much earlier than the time society needs them. So it drives and it accelerates the innovation. So CERN and industry have a very special relation. Here you can see what CERN needs and what we need to buy and what we develop together. So you see that we need civil engineering, of course. We have to build these underground tunnels. CERN has 80 kilometers of underground tunnels filled with technology. We need magnets, we need electronics, we need vacuum components, we need cryogenics, we need materials, etc. So every year, CERN spends about half of its budget to purchase supplies and services, mostly in high-tech industry in member states. And usually, because the technologies are new to industry, we develop together with industry prototypes at CERN, and then when the technology is mature, it's transferred to industry for the production, massive production of thousands of pieces. So it's not a client-supplier relation, it's a real partnership where we grow together, we develop things together. So Portugal and, sorry, I'm going in the wrong direction. Don't look at the slides because it should be a surprise. Portugal and CERN. So Portugal joined CERN in 1986 as member states, and at the time, José Mariano founded LEAP, which is a fantastic structure, very successful, which many other member states would like to reproduce also in their countries or have tried to reproduce in their countries. And it's really at the foundation of the success of Portugal in particle physics, success recognized on an international level. Today, some 200 scientists work at CERN, as I said, and Portugal works in many directions. First of all, on experiments, not only the LHC, but also other experiments of the CERN program, which I didn't have the time to discuss because of reasons of time. It works on R&D for future accelerator, for future technologies, for instance, in the medical field, for medical application, and has also been very active in training and education initiatives, exploiting very much the opportunity that CERN offers, and has very good industrial relations with CERN. So here you can see, I don't want to go into the details, but that's some example of the contributions of CERN to ATLAS and CMS, the tile calorimeter and trigger for the electromagnetic calorimeter of CMS. And my last slide before the conclusion, I've tried to capture here the societal benefits to Portugal in terms of industrial return. So Portugal industry being involved in high-tech relations and collaboration with CERN and building high-tech components. The training programs for engineers, technicians, high school teachers and young students, and the participation of the younger students in master class. Portugal is one of the member states that is benefiting mostly of the opportunities offered by CERN. So let me conclude with this nice image of the sky taken by the James Webb Space Telescope. You remember it was launched a couple of years ago, 2 years ago, or last Christmas, I don't remember exactly, 1 or 2 years ago. So when we look at an image like this one, we are all clearly fascinated by the stars, by the galaxies, by the luminous objects. They are beautiful. However, for us, particle physicists or scientists, astroparticle physicists, cosmology, what is most fascinating is the vacuum and the dark. The vacuum is not empty in physics. The vacuum is full of energy and is full of particles flashing in and out, and it brings a lot of mysteries still. And the dark universe is a question mark. So the dark universe and the vacuum are the next frontier of knowledge. Thank you. Not clear what I'm supposed to do now. Should I ask questions to you or you ask questions to me? Sara is coming. Good. What do you want? Come close.
Hello, good afternoon. I am Sara Sá, I'm a journalist, and I'll be joined on this mesa redonda, I don't know how to say in English.
Round table.
Round table, of course. By José Antão. He's also a physicist, and he's, right? Yeah. Kind of. He, in his soul, he's a physicist.
Not a physicist, but I work with the CERN on the industrial relationship.
Yeah. He's at ANI, Agência Nacional de Inovação, e Ricardo Barrué, who's a physicist. A real one. His whole body is all quarks and protons and electrons of a physicist.
Yeah, we all are quarks and electrons, right?
But yours are from a physicist.
Yes. They put me in tech.
He's on his PhD, working in physical particles and with some work in CERN and some work at LIP, Laboratório de Instrumentação, Experimentação em
Física Experimental de Partículas.
Física Experimental de Partículas. É que a sigla engana.
It's a typical particle physicist acronym. It hides letters and meanings everywhere.
It's not a true one. So thank you again for joining. It's a very good surprise to see this room full on a Friday evening. I thought I was going to be very cold because I thought the auditorium would be empty, but I should have known from the history of all the events that take place here that are always a big success. So thank you. Anyway, thank you for coming. So Fabiola, I'm letting you take your breath now. I'm going to talk to the guys first, okay? So Ricardo, we all know the numbers of CERN. Fabiola has just given us some numbers, but nothing really translates how massive it is, the impact of going there for the first time and getting into the tunnels. How was it for you?
It was you feel very small, you know. Okay, we all look into the stars at night. Let's say it's a similar kind of vibe, but instead of looking at the big sky, you are looking at a machine that weighs as much as the Eiffel Tower. It's 100 meters underground, so it's quite humbling, I would say.
So were you there at the tunnels, right there were you?
So
inside?
not exactly in the LHC tunnel, but I visited, I think, all of the LHC experiments, and it's a very similar feeling for all of them, and it's incredible.
When you decided to be a physicist, was it your plan already to go there and work at CERN? which is the best place on Earth to work as a
Yes.
physical
As
particles.
a particle physicist. Also, LIP is also a great place to work. LIP, CERN, it's beautiful.
Yes, yes.
Uh,
The best place in Portugal would be LIP.
LIP,
The
for
best
sure.
in the world would be CERN, okay? Can we agree on that?
Yeah, we can. I think that's a fair assessment. So, sorry, could you remind me of your question?
If it was your goal when you wanted to study this area on this field.
So I think I was one of the, let's say, few fortunate ones that when I entered university, I already had my eyes on CERN. So this was 2013.
So it was, yeah.
Not that long ago.
So well done for reaching your goal.
Yeah, it's a lot of blood, sweat, and tears, I would say.
Okay, José. So you are the person to promote cooperation between the Portuguese industry and CERN. How does the Portuguese industry take this idea of cooperation with CERN, and is it ready? Because we know we are talking about cutting-edge technology, probably one of the hardest missions for mankind to fulfill, competition, very competitive. How is the Portuguese industry fit for that? How fit it is?
Well, of course, CERN, like other big science organizations, operate on the frontier of technology in many technologies. And that's part of those 500 million Swiss francs that was talking about. But CERN doesn't buy only high-tech things. It buys many things. And the Portuguese companies, some are more ready to use CERN as a client, like other clients that they have in international markets. Some are more interested in strategic partnerships and in more high-tech components, but typically on lower values, the ones that we can have there. Now, we have several smaller companies that we have been nurturing throughout the years. For instance, the ones that benefit from our membership in ESA. And in those cases, because we have the geographic return of the investment the country does there, there's some, let's say, nurturing of the companies that can grow a little bit. Now, CERN is the next step, which is they also have the opportunity to work in very demanding environments and developing high technologies, but there's no commitment to geographic return, so it's more competitive than it would be with ESA. And so the challenge is mostly for the national system to organize around these companies and to support them domestically as well as in the tendering procedures. So it's a long way to go at your question, but we do have companies that can operate in niche parts of what CERN needs. And we have some structure in Portugal that we're trying to arrange so that companies have more support to help developing that.
I think it's okay to give names. Do you want to give names and concrete examples of companies doing specific kind of?
Well, we have
the most relevant companies, at least.
Well, the ones that have been doing contracts, like competitive contracts. We have, for instance, the latest one is A Silva Match. They make helium tanks. So they have just got a contract this year. It's 1.4 million
so
euros.
So it's hard industry.
It's hard industry, but it's not the same as making a tank for transporting wine or milk, right? So it's different. So they are the latest contract that we got. We also got some cabling assemblies that were made this year already. Last year we had this large structure for a neutrino detector, and that was done by Steel in its DST group in Braga. We had power supplies, like pulsed power supplies. That's a company which is a spin-off of Isel called Energy Pulse Systems. They also got these several contracts for power supplies. So it's a mixed thing.
Diverse.
And then we have some companies which are trying to develop collaborations in R&D and technology transfer. Like we have one we've been negotiating with CERN. It's called Lusospace. They also have been approaching and being approached by CERN. So there's a few companies that are dealing with that.
Already, okay, thank you. Fabiola, from the start of your Director General, of being a Director General, you have always been concerned about outreach. It's sort of a passion, and probably I would say it's a mark that you will leave, and there's the Science Gateway to prove it. Why was it so important from day one to show CERN off? And CERN, just to make a context, CERN receives 300,000 requests for visits every year. They only have the capacity to receive 150,000 people, but imagine it's much more than most very famous museums in the world. So, two questions on the same one. Why is it CERN so successful as attracting students and teachers and regular public, and why for you it was so important to increase the outreach and have a dedicated building to outreach?
Yeah, thanks for the very good question. So first, why CERN is so attractive for the public? I think it's I will say for two main reasons. First of all, what we do. What we do, as you have seen, maybe the presentation was of course short, but it's to try and understand how things work, how the universe works at the most fundamental level. And this is something that fascinates everybody. We all want to know where do we come from, where do we go. And so I think coming to the place where we try to disclose the mysteries of the universe, it's something that, of course, attracts everybody, the more senior people or the young people. So I think this is one reason. The other reason is that I think nowadays there is the wish by everybody. We live in a world where there are problems and problems, geopolitical conflict and challenges and climate change and wars and. So there is a need of seeing something positive, of seeing, a place where people are working together peacefully to help humanity push back the limit of knowledge. I think it gives a good message, and people want to see this nice example. In particular, CERN is a great success of Europe, and as we were saying before also, there are not many fields in science and technology where Europe overcomes the US and China. So clearly CERN gives good messages. Now, why outreach is so important? I think for various reasons. The first one is because what we are doing at CERN is not for us, it's for humanity. I mean, when we improve our knowledge of how things work is for everyone. We are funded by public money, and I think it's a duty to share with the public what we are doing with the money that is being invested into CERN. It's also important to attract more young people to science, to STEM, science, technology, engineering, and mathematics, because we know today that, with the technology evolving so fast today, the number of jobs in STEM fields increases in Europe and the US 3 times faster than any other job type. And yet in Europe, only 20% of the students after high school decided to study STEM at university. So we are not really preparing tomorrow's workforce. So CERN can also, infuse a passion for science in the young people. So this is also, I think, very important. There was a fourth term that I forgot, and I will come back later, maybe. These are the reason why I think it's important to know. And then the other important thing, the fourth one, is that unfortunately there is still a lot of mistrust in science in the general public. So, showing what does it mean to do science and how do scientists work, the scientific method, I think it's useful also to increase the trust of the citizens in science. And we know that we cannot hope to address today's challenges from health to climate change to energy, etc., without the help of science. So we have to trust science, we have to work in science. So I think these are the reason why, for me, it's important that we scientists communicate more and better.
Thank you. There will be opportunity for questions from the public, so I'm not sure how the microphone will work, but I guess just let us know whenever, if there is any question. Otherwise, we will keep on talking, but just let us know. Is there a question? Oh. You'll receive the microphone.
When will the FCC will be built?
For sure, you will be able to see it and maybe to work on it because you are young enough. So it's a very good question. At the moment, we are doing a feasibility study because it's a very ambitious project. So we have to understand if it is feasible geological. It looks like the geology of the Geneva and region, the Haute-Savoie in France, is a good region to excavate such a big tunnel. We have to understand the technical challenges, if we can, of course, address them, the cost. If everything goes well and if the project is approved, because it's not yet approved, then construction should start in 2030 and operation in 2045. So the question now to you is, how old will you be in 2045?
Years old.
How much?
35 years old.
Oh, perfect. So you will be recruited to work on the FCC and to contribute to understand how things work with the FCC. Good.
Yes.
Mais questões?
Hello. My question is, you said that CERN reached 10 to the minus 12 seconds from the Big Bang. Is correct? No. 10.
Yeah.
Yes. Would it be possible to reach, how close could we reach, 0 seconds possibly?
We don't know. We don't know in the sense, well, the higher the energy of the collision, the higher the temperature that you can reproduce in your lab, and so the more you can go back in time. So we will continue to develop the technologies with the future colliders and future machine to make some step backward. The thing that we don't know at all today is what was there before the Big Bang. We don't know. We don't know. There are some pre-Big Bang theories, but we don't know what triggered the Big Bang, if it was a quantum fluctuation in vacuum. And there, of course, we start to enter a territory which has to do with metaphysics, philosophy, religion, etc. But I think it will be very, very difficult to go back to that level. But who knows? Never limit the human capability.
I have it. Okay, so I have a two-part question. First is for the proposed FCC, which would be the estimated collision energy that you were theoretically aiming for? The collision energy of the...
Thank you. So the FCC will actually have a two-stage. A little bit would be if it will be approved and built, yes, of course. It will be a two-stage collider in the same tunnel. So you build a tunnel, like we did in the 27-kilometer ring of the Large Hadron Collider. This tunnel was used in the past until the year 2000 by another
LEP, right? Yeah.
LEP. The Large Electron Positron Collider. So it was an electron positron collider, and then in the year 2000 we took out the machine components and we installed the Hadron Collider. So FCC will also have two phases, most likely, two stages. First, an electron positron collider, which will allow us to study, in particular, the Higgs boson with extremely high precision. As I mentioned before, the Higgs boson is a very special particle. It has features, completely different features from all other 16 particles that had been discovered before, brings a new force. And as I mentioned, is related to the very primordial stages, instance of the universe, and probably also to the fate of the universe. So it's very important to study these still very mysterious particles in all details, because this will give us clues and hints to answer on some open questions. And then it will be followed by a proton-proton collider, which will allow a factor of 7 increase in energy compared to the Large Hadron Collider. So it will be a jump by a factor of 7, which is quite substantial.
Okay, that's just a second part of my question, if I can, or, okay.
I think
Okay,
there was a
Professor Qual.
question here waiting.
Hello. I would like to ask you a thing that I think many people has in mind. When you work in the point of breaking and going in the more original part of the matter, you never think that it could happen anything wrong for humanity in generally, that science could reach a point that was of non-written, like produce a kind of Big Bang or Big Crash, anything. No, because in a recent film with the name Oppenheimer about first very big bomb, the scientists had that question in mind. They were sure about 95% that it would be okay, but remained always in their mind maybe 5% that if it does not work as we wish.
Okay,
that's the question I put you.
Thank you.
And to the other.
Thank you for the question, which is of course very good. So first of all, I mentioned that when we collide our proton beams, we reproduce the temperature of the universe, so the energy corresponds to the temperature of the early universe, and it is a huge amount of energy produced. But this amount of energy is confined in a microscopic space, so it's very concentrated. Macroscopically, that energy is nothing. It's the energy of a mosquito, so it cannot really harm. And it's very important at the level of elementary particle, but macroscopically it's nothing, okay? And the energy of the cosmic rays from which we are bombarded every day is much larger. So, and for the moment we are still here. Nevertheless, the answer is that, no, I just want to mention that when we switch on the LHC in 2008, 2009, there was not much, much publicity and much news on the media, on the press. And then someone invented that the LHC will create a black hole which would eat the planet and we will disappear. And the day after we were on all newspapers. So for us it was a great publicity. Of course it was a fake news because we are still here 20 years, not 20, 15 years later. But just to tell that these kind of things, these are things that were, in some sense, proposed as fake news. And for us, actually, it brought us, it turned out to be very good publicity, I must say.
Just to claim, I was on maternity leave on 2008, so I didn't write it. I didn't write this news. So I was going to give you a challenge to, I understand that Fabiola is very attractive to make questions to her, but please remember the other members which are also very interesting. So I dare you to place questions to the other two members of the panel. If you don't, I will. So, but there, I think someone.
Yeah, hi. I had a question. It's not necessarily for Fabiola, but it probably will be. It's more of a technical question. I was just wondering if the future collider, the FCC, will have enough energy to be able to detect gravitons, and if not, what would be the priority in terms of theory confirmation or denial? Like what is the main theories that are supposed to be verified or disproven by the future collider?
I think I can try to go for this one. So I think one of the main things that we want to look for in the FCC, so we have seen now the Higgs boson interacting with some of the standard model particles. So some of the heavier quarks, not the quarks we are made of. That interaction has not been experimentally verified. But one thing that we are very interested in, and this one of the key features of the theory, is that we want to see the Higgs boson interact with itself. Okay? And for this we need a lot of data, and we need a machine that can provide also collisions at high energies. So the FCCHH will be one of the main candidates to do this. This was one of the answers, I think, Fabiola.
Yes, very good, excellent.
Thank you.
And in general, so again, maybe I could say something. So you ask about what theories, what... and I think it's important, of course, if there are theories that predict the new physics, like supersymmetry, gravitons, for instance, is related to theories where the scale of gravity is lower than a Planck scale, etc. It's good also to verify if these theories are correct and looking for these particles. However, we don't know what nature has decided. Okay, so we use the theoretical models to drive the optimization of our detectors, our instruments, because these are benchmark models. However, we should remain very open in our exploration. Our instruments must be able to detect any new particle, any new phenomenon that nature may have decided should exist. Okay, so my way of reasoning is more on, there are open questions. For instance, we don't know what dark matter is made of. There are different theories, supersymmetry, axion, etc., that give good candidate for dark matter. But we have to look, we have to look in an very open way, because nature may have decided that dark matter is made of a completely different type of particles. Okay, so this is also very important to keep in mind.
Okay. Hi, I just want to ask if, what is your environmental impacts? Because to reach those low temperatures, you need to emit heat. Yeah, that's my question. What are the environmental?
It's for you, Fabiola.
Yes.
So, environmental impact. So, first of all, CERN, if you want to know about the environmental impact of CERN beyond what I'm going to answer to you in a few seconds, you can go to the CERN webpage. Since now 4 years, we have been publishing 2, and this year we published the 3rd one, 2 public environment reports. These are documents that are accessible to the full humanity. You go there and you click. And in this document, for 11 environmental domains that go from conventional waste, water, electricity, CO2 emissions, carbon emission, etc., we describe what is the impact of CERN on the environment, and we set ourselves goals to reduce this impact, which is small, but we have to reduce it. Of course, we have all to do our part in this. We set ourselves ambitious but realistic goals to reduce our impact. Our CO2 emission is relatively moderate, small, because our energy comes from France, which is nuclear plants, so it's not renewable, but it's carbon-free. Okay. Our efforts are made to essentially to reduce our impact on the environment, but especially to reduce our energy consumption, because this accelerator consumes energy. And although our energy is carbon-free, nevertheless, energy is a very valuable utility today, and so we should all try to reduce. So what is our strategy in this is, 1, reduce energy consumption by optimizing, developing technologies that allows us to consume less energy. One thing. Second, reusing energy. So, for instance, there are scientific and technical installations at CERN which produce some heat, which is not used. So, for instance, you cool the Large Hadron Collider, and then you produce some heat, and this heat goes in the atmosphere. The idea now is to reuse this heat to heat the buildings on the CERN site, or to heat the buildings in a village in France. And these are 2 projects that have there. So reusing the unused energy. And the third direction is to develop and to push the development of certain technologies which can help society protect the planet. There are several technologies. I mentioned one en passant, and was we develop superconducting cables to bring current. Superconducting cables add advantage to transfer and to carry current without losses. And they're also much thinner than normal cables. And so they can be used for air transport, clean air transport. So this is an example. But we are, and every year we invest millions of Swiss francs out of our budget to contribute to this work to protect the environment and to develop the technologies to help society protect the environment.
Is there a question for José?
Sorry, yes,
Is it for José?
I have a question for José.
If I could add just something before to what Fabiola said. So not just from CERN, but also from all of the community. So from individual action to experimental groups, there was very recently also a sustainability reflection document from the community to just really bring everything together, because the community and CERN, we are very concerned about this. Also for me as a young person, I don't want to be swimming in 2055 or 2060 from melting glaciers. So there is this concern about sustainability and climate change.
Well, I have two questions to José, because I see that the audience here is mainly physicists. And one is, do you track the CERN trainees when they come to Portugal, if they open startups, or what are their career path? That is one. And the other, you mentioned a very successful company, Silva Matos. I remember 20 years ago, in fact, they transported milk. That's what they did. And it was a huge challenge when they won the competition to produce the big tanks for liquid helium. And they had to build a new factory for that. And that was a huge amount, and that launched them into the international market. Are there any other examples like this, so flashy?
Yeah. First, thank you for both questions. I'm going to go there, but also to add to the environmental impacts. I think there's also something that can be said on the procurement side, which is they're also mapping the emissions related to procurement at CERN. And when they do that, the thing is that not only CERN can look at what they do inside of CERN, but look at all the supply chain, and this then can have implication for how companies that want to supply CERN will act to comply with the environmental demands. So this can go much beyond the campus of CERN, can go back to the countries. So now going to your questions, I don't even know where you are anymore, but okay. So the trainees that have gone to CERN, that's a great question. I think that's a very good resource that is being underexploited, I think, by the country. Most of the trainees have not done that, what you have just said, come back, make startups and something like that.
José, I'm sorry, just maybe some people might not know what it is, the trainee program. Can you just summarize what it is?
I think you were referring to the FCT trainees. Okay, so this is a program that was managed by FCT until 2019. It has been discontinued. And this would send young engineers to CERN to work on a project for 1 or 2 years, not just to CERN, also to ESA and to ESO and EMBL, I think.
Other international scientific organizations that the country is part of.
Yeah, so they would have a scholarship to go there. They stay 1 year or 2 years, work on those projects, and then afterwards they would just do whatever, right? So I don't think there was a concerted effort to bring them back and create the conditions to start new companies. I think a few people did, especially the ones that did that with ESA, because also ESA is a much more industry-oriented organization than CERN. CERN is a large research infrastructure. Currently, we don't have that resource anymore because it's been discontinued, but we at the Innovation Agency are trying to find ways also with ICEP to try to revive that a little bit and to work more with Portuguese companies to help establishing those relationships. Now, the other question you asked was about Silva Matos and other companies. I think Silva Matos is kind of an interesting example because they did get into the market with different big science organizations. So they sold to CERN, but then with those capacities that they developed, they also supplied ESO, the Max Planck Institute for Plasma Physics, so for the stellarator for nuclear fusion. They also supplied fusion for energy for this tokamak in Japan. So they supplied several different organizations. Now they got another contract with CERN to do the same thing, basically. I think in terms of business volume, I think the most impressive would be maybe ISQ, and mainly in the nuclear fusion market. Of course, ISQ has done a lot of inspections on the LHC magnets. Then they transferred that same capacity that they developed there to do that with ITER. They just renewed that contract this year. It's a 16 million contract. So overall, they're reaching close to 40 million euros in business with ITER, which is a big number for a country like Portugal. But they're also doing things with ESA, with ESO, also in that kind of activity. But we have others, but these would be maybe the most impressive ones.
This is something on procurement that Jose also mentioned this morning in a presentation that he gave in our meeting. The thing of working with CERN is not just the financial volume of the contract, it's the fact that working with CERN, because of the very stringent requirements and the very push technologies, allows the companies to develop new market, to increase their technological level. It is a mark of quality. There was, I think, a survey done in 2017, and by the way, it should be redone, of 700 suppliers, which clearly show that. And maybe I would like to tell you, since it's Friday evening, an anecdote, a real thing that happened recently. So there was a small company in one of the CERN member states, not Portugal, another one. And this small company was trying to get a contract, bidding for this contract, with a facility which was being built in that member state. And they were trying, and the procurement people in this facility were asking more and more questions. How are you doing this? How are you doing that? So it was very painful, and the guy from the small company was a bit upset of this. One day, since this small company was a supplier of CERN, one day this guy was at CERN, and he receives a call from the guy at the procurement office at the facility, who wants to talk to him, and the guy from the small company says, look, can I call you back because I am at CERN? Ah, says the guy, you work with CERN? And the guy said, yeah, we are a regular supplier of CERN. Ah, okay. 5 minutes later, he calls and said, the contract is yours.
It's a quality stamp, definitely.
I've got a question. I'll go a bit off topic, but I think it will be really interesting once we have such prestigious scientists here. My question is, how should we fight off the conspiracy theories? And mainly once it's CERN, it's such a birthplace of so many funny conspiracy theories. But my question is, how should we fight off these conspiracy theories, like flat earth? In your position, how would you fight it?
Aliens, it's just like aliens. The pseudoscience, the conspiracy theories, how to fight it.
I don't have a recipe like that, but this brings us back to the first question that Sara asked me. I think the best thing we can do is to help everyone. I mean, I think conspiracy theories and all this fake news can be fought, can be dismantled if everyone and each one of us really think and reasons according to scientific method and scientific evidence. So the best thing that we can do, scientists, we can do is to try to share with the public what does it mean to, what kind of approach do we have to have when we learn about something that, well, looks a bit strange, but okay, do we accept it? No, let's go back and understand if there are other news like that. Is this based on facts or just on speculation? I think the best way of addressing these theories and fake news is to try to be rational and apply the scientific method of making sure that what is stated is based on facts. But even with that, we will not be able to to ban them completely, because it's intrinsic, I think, to the human being, you know, the wish of doing something esoteric, strange. So I think a fraction of these things will remain. For me, what is more important is to make sure that there is trust in science. Then afterwards, if people, when they're at home, they want to do their esoteric things, okay. But trust in science, it's very important for the future of humanity.
Also, to think that I think it's important to, as Fabiola said, to know that this has limits, because a lot of these fake news, at least, I mean, I'm talking in personal opinion mostly, but fake news are also something very of the emotional part. So there's like this mistrust that people, they cannot really explain why, but they don't trust scientists. And one can try, first, I think, scientific method and trying to explain and to talk to people, not just thinking about fighting, but really talking. But then also understanding that when it gets to the part of the emotions and the tribe mentality, because you know, these conspiracy theories, they don't show up by themselves and it's one person. So it's Reddit forums, it's pages. So really trying to, understanding, okay, this person it's more of an emotional response than a rational, because then the emotional, it's what just blinds everything else. But I think that's, if you can try to go there, like the emotion really, I understand your concern, blah, blah, blah. I think this is important, but it has much more limited action, but it also works. It also can work, but it's much more difficult.
A question to Dr. Gianotti, please. Who are CERN's top competitors? Do you cooperate with them? How does CERN differentiate itself from the others? And finally, what else would you like to achieve during the time you have still ahead of you at CERN?
Yeah. So so first of all, in science, there is very much, we have very much a collaborative approach. So we work together. Of course, there is always a bit of competition. We call it co-petition, so competition with collaboration. Okay. So because competing is good in the sense that, for instance, at the LHC, Atlas and CMS, the two main largest experiments, there is a sort of competition. They work together, they combine their results, but there is a competition. And this is good because it pushes people to do their best, to be fast, to be better, etc. So this is true also at the level of laboratories across the world. We compete, but at the same time we collaborate. I think it's very good that in our field now, today there is a little bit of, how to say, global optimization of the field. So for instance, at the moment, CERN is the leading laboratory for what we call the energy frontier, because we run the Large Hadron Collider, which produces the highest collisions in the world. So all the scientists from across the world who want to work on the energy frontier work at CERN. So we have many colleagues, a very huge community from the United States, which is our most important non-member state partner. The United States at the moment, on the other hand, are building a new facility to study neutrinos, which are very exotic and interesting particles. And so the European community interested in working on neutrinos goes to the US or also to Japan, where there is another project like that. So if you want, there is a cooperation, because we also try to, because these facilities are complex to build, they are technologically very challenging, they are expensive, we try to avoid to have two identical facilities. Okay, so we try to optimize the field. Concerning your question about what I would like to do in the remainder of my mandate as Director General, which will end at the end of 2025, I think for me what is very important is to make sure that the Large Hadron Collider, which is currently in its run 3, so the last period of data taking before it gets upgraded, so that the third and last period of operation of the Large Hadron Collider is successful, as the first two periods were successful, and that we prepare now for the upgrade. So the Large Hadron Collider will be upgraded to operate with higher intensity of the beam, so that this is also successful, and to complete the feasibility study for a future circular collider, because based on this feasibility study, I mean, the feasibility study will be one of the elements to decide whether the project goes ahead or not.
Well, our schedule was 7:30. I don't know what. And we have time for that. Okay. 4.
So since we are running out of time, the two people here will ask, both of them will ask a question. Then if Fabiola can answer both, then another two will ask a question if Fabiola can answer both. It's okay with you?
And yeah.
Yeah, but I think it's for Fabiola, I guess.
We're not respecting parity here.
Yes.
Where's parity?
Me and Jose are just excited to be here, excited for all the questions. We think it's very important. We're drinking, we're
You've
staying
taken your
hydrated.
pictures already,
yes.
so
No, actually, not yet, not yet.
So what is the question? The microphone. Yeah, the microphones. But first I would like to have the question. Before I answer, I would like to have the question. No, because it's...
So, hi everyone. Can you hear me well?
Okay. Yes.
Hi, thank you for being here, first of all.
Thank
and
you.
for advancing the frontiers of science and knowledge. So, I guess what I would like to ask is, or rather, we are trying to build better these marvelous pieces of engineering with collaborative environment that it's, well, amazing. And they try to detect and refute this theoretical work, right, that's being done, this fundamental quest for knowing the true nature of, well, the nature of everything. And I guess my question, and they've been working quite well, right, with the Higgs boson and all other stuff. And I guess once we start exhausting the low-hanging fruits and the theories, the theoretical physics starts to become harder to prove, will we need to build ever grander colliders? And will we ever actually exhaust colliders, and will there be any hope for physics by then? I know it sounds quite dramatic.
Okay, so thanks for the very good question, which actually requires a little bit of an articulated answer. So first of all, as I said before, we are not running behind a specific theory. We are trying to answer questions, and the questions today are very clear. Obviously, making progress in our knowledge also allows us to refine the questions and to understand if the questions we ask today are the right questions to ask, in some sense. You see what I mean? Huh? Every time you discover something new and you progress in your knowledge, you are able to understand what is still, what you still need to answer and what are the main issues and challenges to address. So we are not really running behind the theory. And the collaboration between experiments and theory is very complex because there are periods in time in the history of physics where theory has been driving the experiments. So there were theories, and those theories have produced, the construction of experiments that have been then validated or not the theory. Nowadays, today, we are in a situation where we are a little bit on a bit of difficulty in theory. So there have been theories that have been fashionable for decades, like supersymmetry, etc., which nowadays are a little bit less fashionable because, of course, there is no experimental evidence of their existence at the scale that we are exploring with the Large Hadron Collider. Doesn't mean that supersymmetry doesn't exist at a higher scale. Okay. So it's a time where we need more experimental input to make progress. So theory and experiments work hand in hand, and there are periods where theory leads and periods where the experiment lead. And today we need more experimental input. So colliders. Colliders, will they be needed in the future? It depends on our knowledge of physics. So I give you an example. The Higgs boson, as I mentioned before, and I hope I've convinced you, is a very special particle, and it's a key to solve some of the current mysteries. Okay? The Higgs boson can only be produced at collider. There is no other instruments that allows you. So today, colliders are still absolutely needed. Maybe in 50 years from now, 100 years from now, once we have understood the Higgs boson in all details and we have answered some of the open questions, maybe the colliders will no longer be needed. But at the moment, they are absolutely essential. We have today a few discovery tools, the Higgs boson, gravitational waves, and supernovae, or primordial galaxies, things like that. Galaxies, I would say, more supernova, primordial galaxies. So these tools are complementary and very important, and we need to build the instruments that allow us to use them. In a century from now, maybe other instruments will be used or will be needed. Sorry, yes. Wells?
I think by the time that the LHC was planned, we were pretty sure that there would be some new physics at that energy scale.
Absolutely.
We expected it to be the Higgs boson, but even in a model-independent approach, we expected to find something new.
Absolutely.
Is it the case that we also expect something new at the FCC energy scale? And if so, what it is? And if not, are there any other approaches, experimental approaches towards new physics?
So the question that we have to ask ourselves is, what is the purpose of the research that we are doing? Is the purpose to find new particles or to make progress in our understanding of fundamental physics? I think it's the latter, although finding new particles allow us to make progress. We found the Higgs boson, we made progress. The LHC, in my opinion, has discovered many things, but there are two main things. One is the Higgs boson, okay? And the other one is that the LHC has allowed us to completely reorient our theoretical thinking. You mentioned correctly that when we switch on the LHC, we thought that we will find new particles. In particular, supersymmetry was the most, compelling theory at the time. And we haven't. And if you look at the theoretical production before the LHC start operation, 95% of the publication were on supersymmetry. Today, maybe 5–10% are on supersymmetry. This means that the theoretical thinking has been reoriented. This means that, and this is revolutionary, the LHC has completely changed the way we look, we think about new physics and our ideas for the future. So it's clearly, and this is as revolutionary as I've discovered the Higgs boson, even more so, even more than that. So you see that what is important to make progress in our knowledge. So I don't know if the FCC will allow us to discover new particles. For sure, as the LHC did and will do, will allow us to make many big steps forward in understanding how nature works. And this is the most important thing. Yes, sorry. Last one.
Okay, so my question was more of a curiosity on something you said on your presentation. You said we have data which tells us that our universe is actually metastable. So which data is that, and how can we infer from it that whether we are or not in a global minima of the potential?
So the data are mainly our measurement of the Higgs boson mass and the mass of the top quark, which puts us in a position, in a status of energy that is not in a metastable situation. So as you said correctly, we are, if the measurement of the Higgs boson and the top quark are confirmed, we are in a situation of not a global minimum, but a local minimum. So we could transient into the minimum. But this depends also on the theoretical understanding, etc. So with the refinement of the theoretical prediction and with the refinement of experimental measurements in the coming years, we will have a more clear understanding if this is true.
I think that's it, right? That's it. Thank you all once again. Have a nice weekend. Thank you.